This is Krishna Malagapati. I am working in St. Peter's Engineering College, EEE department. So here in this video, I am going to explain silicon control rectifier. In the last video, we have discussed power diode, all details. So the continuation of that class is silicon control rectifier, the second switching device which we are using in power electron circuits. So the basics of silicon control rectifier. So this was developed in General Electric Company in 1960s, and the name suggests something to us, that is silicon controlled rectifier. This is associated with three terms. So silicon, this device is made up of silicon material, and you can see this rectifier means based on the application that we are going to use this device, that is called rectifier. It is more popular in usage of rectifier, means which we are going to convert AC power supply into DC power supply. And because of three terminals available for this device, the extra terminal, that what we call gate terminal, is there for the device. When you compare with the diode, then what we call this gate terminal is made for controlling purpose, means whatever the output values that you are getting from that device will be in terms of control values. That's why this device is called silicon control rectifier, and this device is associated with thyroid device. Hence, this SCR is also known as thyristor. Means we can call this SCR belongs to thyristor family also. So we'll see the symbol of SCR first. Symbol of SCR. Symbol of SCR. This is same as diode. Get this? Same as diode. Okay, diode having the two terminals, anode and cathode. So diode having the two terminals, anode and cathode. The extra terminal that we are having for SCR is gate terminal. This is gate terminal. So we can say silicon control rectifier is a three-terminal device. So we can see that three terminals in its symbol. Okay, coming to structure of this SCR is, look at this structure. This is P plus N minus P and N plus. Look at this. The combination of P and PN, different types of materials, P material, N material. So two P materials, two N materials, when we sandwich them like this, the structure of SCR will be seen. See this side we have the anode, this side we have cathode. This is cathode terminal, this is anode terminal. So and here it is gate. Okay. So upper terminal is anode terminal, bottom terminal is cathode terminal. Then so near cathode there is a gate terminal, and this is also called cathode gate also. Other name for this terminal is cathode gate. So this is the structure. Look at this structure very clearly. See this P plus N minus P plus N plus. What does it means? P plus means it is highly doped material. Basically, it is a P material but highly doped material. And N minus means it is lightly doped N material. Lightly doped N material. And this portion we can call drift layer. Drift layer. Drift layer means which allows the voltage to that next portion of the device. Means when you make this device with the lightly doped material, it is easily allow the values from P material towards to the N minus and to the next junction. Okay, and so there are four layers, and we can say junctions J1, J2, J3 junctions. So this is a four layer, three junctions, three terminals device. So these are the four layers, three junctions, and three terminals device. Okay. Then we'll see the characteristics of SCR. Okay, we'll take from its symbol. Otherwise, we will go for we can explain the operation of SCR with respect to symbol and structure also. So we can take this symbol. Then, so see, I am connecting one source to anode and cathode terminals. Plus minus VDC and this is connecting this here is a variable, right? See this, this is another source, another DC values that we are applying across the gate cathode terminals, whereas positive of the battery is connected to the gate terminal here and negative of the battery is connected to the cathode. Look at this, and we can insert some resistance also here. This is a switch. Switch, yes. We can call this source is VGK, voltage applying across gate cathode terminals. And the other name for this VDC also VAK. We can call this as a VAK. VAK means voltage applying across anode and cathode. Look at this. This is one potentiometer. This is for protection purpose, which can provide the protection against the I currents, which the I currents will flow through the device. And here also to control the gate current, we are keeping one resistance here. Okay, let us see the operation. See, SCR operation involves three modes. The first one is forward blocking mode, forward. one is forward blocking mode. Second one is conduction mode. Conduction mode. Third one is reverse blocking mode. So three modes of operations are present for the SAR. So three modes are forward blocking mode, second conduction mode, and the last one is reverse blocking mode. We'll see how the operation is going on, and based on the operation, what are the characteristics. So we'll take characteristics here. We'll take characteristics here. Okay. On x-axis, I am taking voltage applying across anode and cathode. So this side minus VAK. On y-axis, I am taking current flowing through the device. That is IA. IA current means the current which is flowing from anode to cathode. So this way, you can say this is the direction of IA. I am calling this current is IA. Okay, and this current is called IG. This current is called IG. So this is our device, right? So we'll discuss modes one by one. First, we'll take forward blocking mode. Forward blocking mode. Forward means first quadrant operation. First quadrant operation. Look at this. So here we are not at all connecting any source to the gate. Simply the switch which we connected here for the gate terminal is open. Simply it is open. Then now what we are doing is we are applying voltage across anode and cathode through this source, DC source. Then what happened here? The current is coming like this. Current is coming like this, entering into the device like this. This is going to be happened in the next stage. See this once this value is increasing. As we know, SAR is a semiconducting device. What happened is initial voltage drop. Till the initial voltage drop, it won't conduct. See, for suppose, for example, from here I am applying 5 volt. 5 volt is applied across anode and cathode terminals. It won't conduct first. 5 volt, there is no conduction takes place, but small amount of current is flowing during this condition. This current is called leakage current, and leakage current in the first quadrant means forward leakage current, we can call it. So till 5 volt we are applying, but there is no conduction takes place, and next furtherly we are increasing the voltage applying across the device. Next I am going to give 10 volt. For the 10 volt also this device won't conduct. For 10 volt also this device won't conduct. I furtherly increase that value to 16 volt, like that, 15 volt, 20 volt, like that, until this period. Suppose the SAR is ready to accept the values more than 15 volt, means the breakover voltage, forward breakover voltage for that particular SAR is 15 volt. Then immediately at 15 volt of forward voltage, it tries to comes into action. But what happened? Until 15 volts, this SAR won't be conducted. Called, we are applying forward voltage, but it does not conducting. It is blocking the current to flow into the device. Thereby, this mode of operation is called forward blocking mode. This is forward blocking mode. Forward blocking mode, and the current which is flowing in the device during this mode of operation is called leakage current. Basically, this leakage current is due to magnetic carriers in the device. Next, we'll discuss the second mode. Second mode is conduction mode. After applying this 15 volts, till we are not on the switch, we are not giving any supply to the gate signal. Switch is open only, open condition only. After that, what happened? We are further increasing the input values. Let us say 16 volt we applied. 16 volt is applied across the anode and cathode terminals. Immediately, our device comes to on state like this. Like these characteristics are takes place. Okay? This voltage is called VFB. This voltage is called where the SCR device comes into conduction state from forward blocking state is called forward breakover voltage. Forward breakover voltage. This is called forward breakover voltage. Look at this. This is the value. This is the value blocking value. Forward blocking value. Then look at this. So there exist two different values of current, and we can say this value is IH, this value is IL. IH, IL. IH means holding current, IL means latching current. So I tell you what are these two. Holding current is associated with the conduction state of the SCR, and it is the minimum amount of SCR required by the SCR to maintain to hold the SCR in conduction state. So when we state the holding current, this is the statement for holding current. Holding current is minimum amount of current required by the SCR. In that case, this SCR will be maintained in on state. And coming to latching current is also associated with the conduction state of the SCR, and it is also stated like this. Latching current is the minimum amount of current which is needed for the SCR to maintain the SCR in its on state even though gate signal is removed. It is very clear for the two statements, holding current, latching current. Holding current, we do not call any gate voltage, gate currents values. But in case of latching current, there is a term called gate current comes into action. Even though gate signal is removed, the SCR must be in on condition, should be in conducting state. So for that, minimum current is latching current. If suppose the anode current is coming back to the holding current, so holding current is the minimum amount of current which we can say the SCR is in on state, still in on state. That's why holding current, latching currents are very important terms in SCR conduction mode of operation. And when we relate these two, IL is equal to the 1.5 to 2 IH value. Means IL value is equal to the 1.5 times to that of holding current. Okay. Now, still we discussed So far we discussed without gate signal for the device, without gate signal for the SCR. Now what I am doing is, I am going to switch on gate signal also. Now I am applying voltage across gate and cathode by closing the switch. After closing the switch, what happened? Current is coming like this and entering into the gate terminal. And now what happened? It's going to be applying gate signal. If two inputs are there, initially one input is there, now there exists two inputs. One input is this one, other input is this one. Therefore, what exactly going inside the device is, when you apply the forward bias, J1, J3 junctions are forward bias, but J2 junction, middle junction is in reverse bias. To break the J2 junction, this all we are going to do. Means applying forward voltage, applying. After applying breakover voltage, forward breakover voltage only, that J2 junction is going to be breakdown. Hence, the device allows the current to flow from anode to cathode. But what happened here? I am initially breaking the J2 junction by applying external voltage across the gate and cathode by forcing the current into the gate terminal to break the J2 junction. Now what I am doing that. So by applying forward voltage, J1, J3 junctions are already in forward biased condition, but J2 junction is going to be breaking down by applying external source here through the gate terminal. Hence what happened? This device, this SCR won't take this much of breakdown voltage values. Then immediately what happened is, suppose I am applying some gate voltage across this, let us say 5 volt I have applied here. 5 volt I have applied here, already 10 volt. Once I applied 10 volt through the forward bias manner across the anode cathode, immediately I applied 5 volt here, 5 plus 10 volt, it is up to rated value 15 volt of the device. Automatically what happens? If further I increase the value immediately, this device is going to be comes into on state like this. At 10 volt of forward voltage, our device comes into conduction state from the forward blocking mode because we are applying extra 5 volt. What the device is required to reach the rated value through gate terminal. Suppose I applied 8 volt. After 5 volt, I increased the value. Let us say this is a variable device, variable source available. We can say RPS, we have that. Then when I increase the RPS value, regulated power supply value, automatically what happens? It reaches to 8 and it comes to conduction state earlier than previous condition. I can call this one is IG1, IG2. Then further, suppose I am increasing 10 volt, then coming like this. This is Ig3. I can say Ig3 greater than Ig2 is greater than Ig1. Means what? Anyhow, the device required value to turn on is above rated value, above forward breakover voltage value. Once the device got that voltage values, automatically comes to conduction state. So what I am doing here is I am applying inputs in two ways to the device. That is, one is through anode and cathode, what I call forward voltage, through gate and cathode, what I call is gate to cathode voltage. So some voltage amount I am giving through this way, other some amount is I am giving this way, so that it reaches the required voltage value to comes into conduction state. Like that we can say, we can discuss this forward side means first quadrant operation. Okay, we'll go for a reverse blocking mode of operation. Reverse blocking mode of operation means we do not use any gate terminal here. We are simply opening the switch We don't discuss about we don't apply any voltage across the this gate and cathode. Just we are applying voltage across the anode and cathode, but it is in reverse manner. Means battery terminals are going to be interchanging. Plus minus minus plus are interchanging. So that what will happen? Okay. We'll see what will happen. This is minus, this is plus. Okay, now what happened is, so this minus polarity is applied to the anode of the device. This plus of the battery is connected to the cathode. This type of biasing is called reverse biasing. Reverse biasing means the SAR device getting the characteristics in third quadrant operation. So now what happened is, so initially there is no current flowing through the device, same as diode characteristics here. Look at this. So when you apply the reverse bias across the device, then automatically it doesn't allow the current to flow from anode to cathode, but due to minority carriers in the device, they carry some leakage current like this. This amount is called leakage current. After applying more voltage, reverse voltage across the device, automatically avalanche breakdown takes place across the device and some voltage applied. That voltage is called reverse breakover voltage. Reverse breakover voltage. After this voltage value reaches to the reverse breakover voltage, then immediately that J1, J3 junctions initially is in, they are in a reverse bias condition. Now what happened is J1 junction breaks down and J3 junction breaks down. Already J2 junction is in forward bias, that it allows the current to flow from reverse direction, cathode to anode. Then what happened here is, but so till this values, when you apply the reverse voltage that much value, automatically there exists a heat effect for the device, what we call thermal runaway. Due to that thermal runaway, the entire device is going to be collapsed, damaged. So that do not apply reverse voltage across the device this much. That's why it is just for critical. We do not apply this voltage practically. Means why this SCR is called unidirectional device. As same as our diode, this SCR is called unidirectional device. Unidirectional device means it allows the current to flow in one direction only. The second one is latching device. Latching device. Latching device means, see the forward bias characteristics. There is a term called latching current. Latching current, holding current are there. Latching current is the minimum current which can keep the SCR in forward bias in conduction mode. Even the gate terminal is removed. Gate voltage is removed. After once the SCR got on state, latching current, if the current value is more than the anode current value is more than the latching current, definitely it will be always in on state condition because of the latching current values. That's why this material is, this device is called latching device. Then bipolar device. Bipolar device. There exists two called bipolar device. Bipolar device. And coming to its applications, as the name suggested, this SCR is using in rectification purpose mainly, and this can be used in other configurations for converting electrical energy from one form to another form, AC to AC, AC to DC, then DC to DC choppers also we can use, and the AC voltage regulators. AC voltage regulators also we can able to find this, and this can be used in choppers also. So in this class, in this video, we discussed SCR basic introduction of SCR, basics, and it's a symbol structure of the SCR and how it is different from normal SCR and power SCR, which is using in our power electronic configurations. Then we have seen the characteristics and its operation. In the next class, we will see the two transistor analogy of the SCR, because the two transistor analogy will give us good understanding of total about the SCR circuit. Thank you.